Well, good afternoon. Thank you for coming to learn about DDoS and building DDoS-resilient applications. My name's Oliver Sturrock. I'm the General Manager for AWS Shield.
My name is Paul. Nice to meet you all. I lead the Shield response team, or two groups. Shield response team that does incident response for AWS infrastructure and our services, as well as for Shield Advanced customers. And then I lead a group of a team that does research, threat research into the DDoS attacks we observe and use that threat intel to build features for you and protect ourselves. So really excited to be talking to you today.
So we're going to talk about how we protect the availability of the AWS network. That'll give you an insight into some of the tools that we use to keep our backbones uncongested and our key services working. Then we're going to talk about how we stop DDoS before the first attack packet. Just checking there are no AWS security people in the room, because I'm not supposed to use the word attack. But we do obviously think about bad actors out in the world. So we do a lot of proactive work, and that's some of the things that Paul's team is doing to proactively block attacks. And then we're going to give you a framework for how to think about getting the best DDoS resilient for your applications using the tools that we provide. So let's kick off and think about some of the things that we do in order to protect the AWS network. You've probably seen this diagram many times. We call it the shared responsibility model. And it means that as a customer, there are some things that you take responsibility for. But as AWS, there are many things that we take responsibility for. So we take responsibility for the security of the cloud, and you need to think about security in the cloud. So a couple of examples of what that means. If you're running an EC2 instance, we take care of the hardware, the networking that connects that to the internet and to your VPCs and so on. But you need to take care of the operating systems, patching, make sure you've got the latest security updates. Whereas if you use something like Lambda, for example, what AWS does for you is a much higher level. And so there's no patching to be done in Lambda. You just simply focus on your application code. Another example would be load balancing. If you decide to run your own load balancers, there's a ton of work you need to do. Whereas if you use application load balancer, that will scale automatically for you. And these are important considerations when it comes to handling DDoS and traffic spikes. So we broadly think of network layer attacks or DDoS attacks in two different categories. One, a network layer 3-4 of the ISO model, broadly speaking, which are the transport and the network. And these are things that are happening at the raw TCP, UDP level, typically unencrypted, whereas layer 7, which is predominantly HTTP but not exclusively HTTP traffic, there are some additional challenges because a lot of your traffic may be encrypted. We can't see inside that traffic, so we've got to take mitigation and detection decisions without understanding the content of that traffic, which creates some additional challenges for us. And so there are some challenges that come from operating a network at AWS scale. There are many, many ways traffic can reach your application. There is no simple single point of ingress. So we've got to cover all of those different places that traffic can enter the network. We've also got a fairly significant monitoring challenge. So we run, I don't know, I'm going to throw out a number, Paul could correct me, but probably hundreds of thousands of autorouters that we need to monitor. And I'll give you some figures that we capture through our monitoring in a second. But also, what's on the destination of that traffic varies a lot. So you could be running a T2 micro instance, or you could be running something like an ALB. There are very, very different scalability metrics that we associate. So we've got to understand all those capacity metrics in order to make sure that we're limiting to the appropriate rate in the event of a DDoS attack. Probably the most difficult problem, I have a joke, which I was going to put on a slide, but I like to say that protecting from DDoS is easy. All you've got to do is work out what's good and what's bad and block the bad stuff. But that's probably the most difficult problem we face, is figuring out what is bad traffic. And Paul's going to talk about some of the threat research we do to help us do that. And then we've also got to find a mitigation strategy that works. Most customers are extremely nervous about false positive mitigations, i.e. blocking even one good packet is extremely unfortunate, and so something we work extremely hard to avoid. How big is big? So these are all metrics that we gather, primarily Paul's team gathers as we do our work. So we see over 1 million DDoS attacks per year on our network. We examine exabytes of data every minute, thousands of DDoS attacks a day. We see, so AMR are the Amazon Managed Rules for WAF, which Paul's team also looks after. We see 100 billion requests on those AMRs per day. And we gather 300 gigabytes of flow log data every second from our networks. And so we got, it's not just gathering it and then sticking it somewhere. We've obviously got to analyze that and understand what it's telling us in terms of what represents attacks.
Awesome. Great. I want to double click a bit on the points of ingress in the AWS network, right? This is where we start. Our starting point is for when we think about protecting against DDoS, where is this going to come from, right? Where is this traffic coming from? I wish it looked like this. It would make my job very easy. It would be super simple. One entry point, traffic all looks the same. It's going to the same place. It's behaving. It's really predictable. You know what to expect. It's pretty easy to just determine what's bad and what's good, right? So in reality, it's not like this. We've got a number of points of presence that customers can, or a number of ways that traffic ingresses. Starting off with the peers, we've got private peering, public peering with exchanges. We've got customers doing direct connects straight into our network. We've got our regional POPs that serve, the whole, kind of connected to the whole backbone network. We've got ways that you can come in through VPNs and mobile networks. With these services, you have your choice of connecting through compute capacity that's sitting on a 5G mobile network, or a rack that's sitting in your on-prem data center, or you could come through via a satellite. These are all points of ingress that we have to think about with all the challenges that Oliver mentioned. Like, how do we monitor all of this? How do we track where that traffic is going so that we can be ready to respond when we see signs of DDoS? Now, once you get your traffic to our network, there's a bunch of different services that you could potentially be using, right? If you're using our CDN, CloudFront, we know what to expect. If you're using Route 53, we know what DNS traffic looks like. Of course, there's a many different load balancer services. That load balancing at the network layer, at the application layer. Global Accelerator has listeners on it, so when you configure your endpoints, it gives us insight into this is the type of traffic you're expecting for your application. There are a few more complexities, though, if you're just running on EC2, right? You could be doing anything. And so again, if we're not aware of what you're running on your EC2 instance, and so when we're thinking about DDoS strategy for an EC2 setup, it makes it just that little bit more challenging. And of course, there's traffic from AWS to AWS that we deal with. How do we make sure that when we see east-west traffic, surges of east-west traffic, to distinguish between what is a legitimate download, maybe from one region to another, or it's more malicious? So in reality, this is what we have to deal with. Just many points of ingress, and we build software to monitor all of the the routers are on this network that feed us the telemetry we use to monitor and detect and mitigate DDoS. Our mitigation systems sit on the border network, and they allow us to scrub the DDoS traffic out without having to shift traffic to some other scrubbing center that's miles away and incurring latency. We can do this straight away inline, and you won't even know that it's there. So these are the points of ingress that we have to think about, hey, what's going to happen? So we have strategies for each of these things. So Oliver, you want to take us?
All right, so let's talk first of all about traffic coming into the CDN CloudFront. So as we already said, traffic coming into CloudFront is predominantly HTTP, HTTPS, or most recently Quick, which is CloudFront announced support for Quick this year. But it's all coming in on port 80 and port 443, which is it's a good start. We can block traffic coming in on other ports. We can block UDP traffic. But we will get a request flood. And a request flood is probably the most common type of layer 7 attack that we see. Around 50% of the attacks that we detect and mitigate are request floods on CloudFront or other layer 7 services. And these will come into a POP. And so we get a lot of logs from CloudFront and other services. And so, we'll touch on this in a little bit more detail, but we've got detection engines that run behind here to look for top talkers, other kinds of anomalies, but principally volumetric. But we've got other techniques, and I'll talk a little bit more about those in a second. And we learn from those. So we use modeling to figure out what these malicious requests are looking like. But one of the advantages we have in CloudFront is scale. So we got 435 or more POPs. That information was correct a couple of weeks ago. It's probably out of date now. Which means that if we get a request flood coming into an individual POP, without you as a customer having to do anything at all, we can use DNS and a protocol called Border Gateway Protocol, BGP, to change the way that traffic is being routed. So we can actually isolate the POP that's under attack, and we can move that traffic off to other POPs. And all of that's automatic, happens behind the scenes, happens very quickly, usually within a few minutes. So mitigating traffic attacks for CloudFront, we use that scale to our advantage to absorb a lot of that and then to block. Now, the disadvantage for you as a customer of this is that that's a fantastic way of making sure we don't drop packets at the POP, but it will get through to your origin. So you've got to make sure your origin is prepared to handle that traffic. So a great tool to make sure that you're only getting the traffic that you want on your origin is WAF. So you can deploy WAF against every CloudFront distribution. And in there, you've got all of the capabilities that you have in WAF. You can use the AMRs to block certain categories of traffic. You can set up your own rules to block traffic that you know that you don't want. And we also have built a tool called Layer 7 Auto Mitigation that uses WAF logs to detect, and then will automatically produce very, very highly tuned specific rules. So we take logs, and even if you deploy a WAF, by the way, on CloudFront or ALB with an empty web ACL, that will enable us to do this. So we're using the logs to examine the traffic patterns. We are using that to create a baseline of what good traffic looks like. So typically we need a few days, the longer the better, but we build a picture of what normal traffic looks like on that distribution. And then we continually monitor traffic against that baseline to do anomaly detection. So we will see things that don't quite fit. Now that could be volumetric. So a change in pattern for that particular time of day, particular day of the week may have changed in an unusual way. Now, you can get flash crowd events, so-called, that might trigger that. So not every volumetric spike is a DDoS attack. So we look for other factors. Is this coming from somewhere different? Are the user agents different to what we normally see? IP addresses, distribution, those kinds of things. And when we detect these anomalies, we build an attack signature, which is a description of that anomalous traffic that doesn't also describe the baseline. And that's the key to making sure that we don't cover false positive detections. And so once we've developed a signature, we test that against the baseline. And if we see more than 0.1% match against the baseline, then we will not deploy that signature. If we get a good match, we don't see false positives, then we'll build that attack signature as a WAF rule and automatically deploy that into WAF. And so this is a high precision tool. It doesn't kick in instantly. It takes a few minutes to apply. So you do want to think about what happens in that intervening period. Can your origin handle that spike in traffic? A really useful tool is to have rate-based rules deployed in WAF that will prevent volume spiking above what your origin can handle. But this is a very high precision tool which will then take out that anomalous traffic and reduce that traffic volume back to normal levels.
Cool. All right, so if you're running a web application on CloudFront, you might be thinking, like, how well protected am I from the lower layer, more commonly seen DDoS attacks? And so I'm going to go through 2 examples now so that I can reiterate that the answer is very well protected. Starting with the SYN flood. Just to quickly explain how this works, TCP has a 3-way handshake, which probably a lot of you are familiar with. It's really a way for a client just to establish trust with the server. It works like this. The first packet comes from the client. It says, hey, it's a SYN packet. I want to establish a relationship with you. The server responds back saying, I acknowledge your SYN packet. I'm happy to talk to you. And then the client will come back and say, great, let's do some business. And from then on, the HTTP requests flow over that connection, right? Pretty straightforward. Well, what we see in the world of DDoS is that a bad actor has no intention of, typically for SYN floods, of completing this handshake. They will just send SYN packets because they know it's compute heavy, right? You've got to, on the server side, you've got to track that SYN packet. You've got to respond back. It takes up computational resources, and can be a very effective way of taking down a resource. So what we've built for CloudFront, and this is part of just Shield's mandate to protect all the infrastructure, is a technology called SYN proxy. So this sits, it's integrated with all of our CloudFront POPs. It's in line all the time, and every single SYN packet goes through this. And what it does on its behalf is got an ability to respond back to these SYNACs, and only when the client actually comes back and formalizes that handshake does the connection be handed off to your CloudFront distribution. So essentially, any malicious connection attempt that bad actors have no intention of doing, they will not even reach your CloudFront distribution. So that is immediately protecting your origin from any scaling requirements or having you to deal with this additional traffic. Another example of these types of lower layer network DDoS attacks is UDP amplification. Very, very, very common. What is happening here is out on the internet, there are many different services that are hosted on the internet that you can just find by scanning, and you hit them with a packet, they respond back with some payload, right? So the way this works, the reason why it's called an amplification attack is that the initial request that comes is generally really small and really easy to send millions of them. But the service, like a DNS service, for example, will respond back with a payload X times greater than the size of the request. And so an attacker or a bad actor will spoof the source IP address of that packet with your CloudFront distribution, and the packet will come, and response will be massively bigger than what was initially sent. And so if this is targeting your EC2 instance, you have to deal with this massive bandwidth of traffic hitting your application now. But because on CloudFront, we know you're running a web application, and you're taking advantage of just the distributed capacity on all of our POPs, we drop this UDP traffic without you even having to worry about it. And as you can see here, these are the amplification factors that one would typically see on average for different types of services that are hosted out there. You can see why Memcache was so deadly back in the day, right? Because the amplification factor is huge. Cool. So I'm going to hand over to Oliver again.
Yeah, so let's dive into DNS. DNS is an interesting area, and we do have customers that run their own DNS servers. I've never really quite figured out why, but it's not a great idea. Because we've done a lot of work. Forgive me, that wasn't meant to be offensive to anybody who does that. We've done a lot of work with Route 53. Route 53 is the only AWS service that has 100% SLA for uptime, which is really hard to do. And part of the reason they can do that is because of the collaboration with Shield. So in the old days of Route 53, where we had, so for anybody who is not familiar with how DNS works, it's a hierarchical system, a kind of dictionary lookup system, where you have an authoritative domain server that will say this is absolutely the connection between a domain name and IP addresses. And then sitting around those things are resolvers that then provide a caching layer. So early on, we would see huge numbers of people attacking our authoritative servers, the root servers, as well as good resolvers. But our attackers would come in and we try and exhaust resources on that server. And so the first thing we did was to say, well, we know what good resolvers look like, so let's build a list of good resolvers and maintain that list and prioritize the traffic coming from known good resolvers. And so we take in request logs, and we have a list of good resolvers that we maintain on a regular basis. And we built a traffic prioritization system in our traffic scrubbing technology, packet scrubbing technology that sits around the edge of our network in all of our transit centers and POPs. And so we assign these 8 buckets labeled from P0 to P7. And we say each of these buckets has a certain number of tokens, which represents the rate at which we can take traffic at that priority. So where we have traffic that we think is low priority because they're not good known resolvers traffic, but it's okay because we can support that capacity, we allow that traffic through, so no problem. And we can absorb, again, very much like CloudFront, Route 53 can absorb huge traffic volumes. But on the other hand, where we are now getting high priority traffic from good known resolvers, we're going to prioritize that. And at some point, we'll run out of tokens. So we'll run out of rate or capacity that we will pass on to the DNS servers. And so you can see the little no entry sign. Packets that we've categorized as P5 through P7 are now going to be blocked. Because if we sent them through, that would exceed the capacity of the target sitting behind. And so that's a way of allowing good traffic through and rate limiting the bad traffic. And that's very successful where you've got a very clear definition of what is good, i.e. in this case known resolvers, and what is bad, i.e. things that are not known good resolvers. So the bad actor workaround for that is to then go and hit the resolvers. Now, resolvers are a caching system, so it relies on if you look up google.com a million times, it's just the resolver's just going to return the same thing. Well, okay, it's going to return a response direct from the resolver without going back to the server upstream. So in order to get through the resolver, you need to use a cache busting technique. And cache busting involves changing subtly the domain name you're looking up, so it's different every time. So we get 1234 ABC. Amazon.com, for example, and we rotate that domain name, and so the resolver will have to pass that through to the back end. So it's a good known resolver, but we're still getting millions of requests from all of these good known resolvers because they're different domain names and it's not cached. So what do we do about that? So what we do is, this is another benefit of our tight integration with DNS, is that we build a filter based on our understanding of what is actually contained in the hosted zone for the Route 53 zone, meaning that if it's just a made-up domain name, we just block it. We drop that traffic. So only the good domains get through to the DNS server. And so that's the way, all cache busting works in the same way. Basically, you've got to sort of come up with some arbitrary pattern, which is going to prevent the cache from doing its thing. And so in this case, we have a table where we can actually drop things that aren't in the hosted zone. So that's how we protect Route 53. That's a couple of good reasons why you should use that rather than hosting your own DNS server. Great.
So let's think about how we look at traffic coming to other types of endpoints. So not CloudFront, not DNS. So here, like we said, especially if you're running anything that's directly accessible through EC2, you could be doing any one of these different types of applications, right? This means any type of protocol we could expect. So it's not as simple as just going, hey, let's just block all UDP traffic that's coming on some amplification source port, right? It's got to be a lot more nuanced. And so our first priority here is to ensure that the instance or the resources that you're using stay available, right? That's priority number one. So that's originally why we built Shield. Just make sure that infrastructure remains available. And so we, came up with this strategy. One of our strategies to do this is to, as soon as a packet comes into our network, obviously it's tagged to some IP, right? We go then and look up what's behind this IP. So you can think about, for every single packet coming in, what is going on? Like, where is this going? Is it, if we're seeing, as we aggregate that data and we go, hey, why are we seeing millions of packets going towards an instance type that can't handle that? Right, that gives us a quick sign of something is not right, and this is most likely DDoS, right? So we look at endpoint capacity as one way for us to ensure that your instance stays available. And so when we place a mitigation, the moment we detect this is going on and we place a mitigation, that mitigation is designed to keep the instance up. Same goes for the load balancers that you might be using, right? Like NLBs, ALBs, for example, are same situation, right? We look at what capacity that can handle. We make sure that that stays available based on with the mitigation that we put in place. And it's okay at the network layer, right? But layer 7 traffic is really difficult to know what is legitimate. There are a number of different types of applications. You may not be running a web application, right? So it's a challenge for us to defend your application on EC2 if we don't know what exactly you're expecting. And then, of course, we've got the challenges of the scale with all of the data that we collect and have to aggregate and parse to ensure that we're keeping our eyes on all the hotspots that are going on in our network and act accordingly to that. And this incurs some delay, right? So our protection for regional resources at the moment, we're around 5 to 9 minutes to detect and place a mitigation. Right? So this is us monitoring traffic coming in from everywhere to an instance. And so that means if your resource might see some degradation of performance until our mitigation is placed. Okay. That doesn't guarantee that your application can scale, right? Or your application can manage the additional traffic that's coming on top of those network connections. But these are the challenges that we face and are thinking about continuously that drive our roadmap prioritization for you. So some things that Shield Advanced customers have over and above just the basic protection that you get being part of the AWS network is NACLs. I mean, everyone's got NACLs in their VPCs. Hopefully you're using them, right? They're a great way to block and not allow things in and out, right? So this is a feature of AWS Shield Advanced where if you have a protected EC2 instance and it's being targeted by some DDoS traffic, we will take the NACL configuration that you have specified, right? So if you only expect a certain type of traffic on a certain port from certain places, we can place that NACL configuration and promote it to the border network. And just every router then on the border network is going to know what your configuration is for that instance. And that allows us to get around some of those challenges of not knowing exactly what you're running on your instance. Then we have a further mitigation capability. This is called Byte matching. This is really helpful if you control the software of the client that's connecting to you. It's a pretty popular technique for us for gaming customers. And so you can then specify You own what's going on in the network packet, right? Because you own the software that's sending the packets. And so you can put in either in the layer 3 or layer 4 headers in the packet or the layer 4 payload, put a sequence of bytes in there, and then we can place mitigations that filter out anything that doesn't have that sequence in it. Again, another way for us as Shield Advanced to tailor our DDoS mitigation specifically for your application. And then the last thing, the next thing for Shield Advanced is health-based detection. So this is a great way for you to influence the detection and mitigation sensitivity levels, right? The way this works is you define a Route 53 health check that monitors the health of an endpoint. You can monitor that with your own custom metrics from your application. It could be a CloudWatch metric like 5xx errors, right? When you get over a certain rate, it then switches to unhealthy. And you associate that with a resource that you've protected with AWS, with the Shield Advanced. And so when health is good, we will collect more data points before we place a mitigation. This helps us prevent a false positive. And also, if your application health degrades, then it increases the sensitivity level and allows us to place mitigations faster. So you won't be subjected to that 5 to 9 minutes. For Shield Advanced customers, we can place it much quicker. All right, so these are some of the tactics that, as a Shield Advanced customer, you can leverage for applications you've got running on.
So, Paul, let me jump in on the 5 to 9 minute thing since you've mentioned it a couple of times. So,
go ahead.
To join up a couple of things we've talked about, the reason that it takes that length of time is that we've got a capacity of a destination resource sitting in a region somewhere. And we've got many different ways traffic can ingress the network. So even knowing that capacity, we've got to distribute that capacity around the network. So we've got to say, we're going to place so much of that capacity in this transit center, so much over here. So it's that rate limit distribution that takes most of that time. The problem would and will be solved with regional protection that's much closer to a regional resource. So we are just entering a private preview of a regional packet scrubbing technique that will sit close to those regional resources where we will get that period under a minute. So since Paul has exposed the dirty laundry, I thought, I'll tell you what we're doing to clean it up.
Thanks, boss. So this is a very interesting challenge that we have to solve. We sometimes respond to DDoS events where traffic is not just coming in from the outside of the network but actually from within our network. Usually what's happening here is that a customer has potentially left their instance just sitting there open to the world. No security groups on it, no NACLs. It's even unpatched and has some vulnerable application software running on it. And if you do that, you should do it as an experiment, actually, just to see what hits your instance is actually a pretty cool experiment. And what happens is it gets compromised, right? Some exploit is, a vulnerability is exploited, malware is deposited. Malware is a software that bad actors write to control your instance. And they install this software, this malware, and now all of a sudden, unbeknown to you, your instance is taking part in a botnet. And
can I just jump in as well, quick? Please don't do that.
Yes, please don't do that. So when this happens, these botnets are operated by command and control servers, right? That's what we call them, C2s for short. And the C2 will send a command, and it'll say, hey, go target some IP address on the internet. And that may be on AWS, it may not be. And these instances that are sitting in the scalable platform are now sending traffic to this destination. It drives up costs for you. That's why we don't recommend it. It also presents, obviously, a risk that we have to manage because it can affect availability and congest networks. And so we have really good DDoS defenses that kick in here. Our first priority is to, because this is happening in our own backyard, we can see it immediately. We can shut down that instance. We can block the traffic. and we can work. We have a trust and safety organization that works with the customer whose resources may have been compromised and helps restore that instance back to what it should be. And so that is no longer part of the botnet. But that's where this fun just starts for us, right? Because this is happening in our own backyard, we've got additional visibility. Right? We have additional insight that we don't have if this traffic is just coming from outside of our network. So I'm going to talk about that in a sec. Another way this is done is if you have a proxy service, right, similar to bots. A proxy is not infected by malware. Proxy services are really common practice in architectures. And so there are proxy services running on the internet that are just public. They open, you can hit them with a request and get proxied from there to another server, which is a great way of getting around some things that can be used maliciously. And sometimes customers on AWS run proxy services that can also be abused, right? Because they could be just open to the internet. And so similar thing, right? We have defenses that kick in and allow us to work with that customer to kind of not shut them down, but like build a better security posture for the proxy so that it can't be just leveraged by anyone on the internet. So as I said, we've got additional visibility. And so I'm going to talk now about how we use this visibility to stop DDoS before it even hits us. And part of our secret here is that we have a time machine. And how this works is that we can see when we have access to NetFlow in your VPC. Don't freak out, because actually you might have noticed that you get billed every month. And the way that billing works is by analyzing your NetFlow and figuring out where your data transfer is going and then accruing charges, right? So when we access what's going on in your NetFlow, it allows us to see, hey, packets are coming from somewhere to this instance. And so we don't manually do this. We've got systems that do this for us so that we don't have to get our fingers involved in any sensitive data. But it allows us to aggregate a view from a DDoS attack to say, hey, all of the instances in this DDoS attack that were involved that sent us traffic all spoke to a single instance in the last 24 hours or the last week. Usually what that means is that common resource on the internet that spoke to all of those instances is most likely the thing that exploited your instance software vulnerabilities and deposited that malware. So now already we know, hey, this is the infrastructure that's sitting out there that's part of the bad actors network that started the compromise of these instances. And we use that as part of a research feature that we've got, which is a network of honeypots. We run like 2,100 honeypots over all the regions in AWS, and they are doing what I just told you not to do, which is leave an instance just open to the world. They just sit there, they listen on every port.
I think Paul told you to do that, by the way, and I told you not to do it.
No. Yes, boss. And so we built the software so that it just responds to anything, right? If you're talking to our honeypots, we know you're not good because you've just scanned the internet to find them. There's no DNS name pointing to them. It's not in our public docs. So you've got to scan the internet to find these. And when you do, usually what we see is the person tries to, in whatever means possible, deposit malware on this instance. And so immediately we go, hey, okay, cool. Here's an HTTP request that's got a wget command in it, sending you to go to some other host on the internet to download the malware binary. So we do that. We go and fetch it. We download it. And now we have the malware from this botnet. And we know that this malware is associated with the DDoS attack that we observed because we know that the common infrastructure was the same thing that hit our honeypots, right? So we can tie DDoS attacks on our network to botnets. So
Well, but we go a little bit further than that, right? Because we will actually execute that malware in a sandbox environment. We see you're getting to that?
Next slide, boss. Next slide.
Nice.
So, yeah, we collect a bunch of intel from these interactions on honeypots, right? So we now know there's someone bad out there trying to exploit our vulnerable applications. Number one, we add that to a reputation list that we leverage in WAF. We use them for internal intelligence, right? We know what their type of exploit was. It might be something that is a common, or it might be a new 0-day. Like when we saw Log4j and Spring4Shell, all these different things come out over the last year, we went to our honeypot interaction and said, oh, we can actually see this going on. Like this is like first-hand intel for us to help understand the type of exploits out there. We also know another server on the internet is hosting malware. Again, add that to reputation lists. We have the malware itself that we can execute. And typically when you execute malware, what happens is in the first stages of it, it will register itself with some endpoint on the internet, right? It's saying, hey, I was successfully installed. I'm here. Please use me for any type of DDoS you want. And so the malware points back to the C2. It gives us a treasure map all the way back to this C2 server that's controlling it. So now we're sitting in AWS with complete visibility into the infrastructure that is behind an attacker, behind a DDoS attack. And so we push this intel, as I mentioned, into WAF managed rules, network firewall managed rules. We also share malware with GuardDuty. And so all of the intel we collect from our honeypots goes into services that you can use to protect yourselves. But how does this help us stop DDoS hitting the network? We cut out the brain. What I mean by that is, when you take down a C2, all of the drones and the bots just are now null and void, right? They can't be used. And so if you take out the brain or the heart, I realize the heart would have been a better image, but if you take out the heart, the whole body of the botnet is now mute. And so what we call this a takedown. And so usually what we're doing here is we're going to other hosting providers and we're saying, hey, here's an IP that's running on your network. Here's all the evidence of the C2 commands that we're receiving from it. Please, can you take this down? Or we go to a domain name registrar and we're saying, here's a domain name that's got a bunch of IPs of C2s. Take the domain down. And so, of course, you can rebuild this infrastructure. You can re-register a domain and get it set up again. But what we are doing by doing this is driving up cost for bad actors when they target AWS. So we may not get all of the DDoS out of the internet. If I achieve that, I'm going to get a raise. But what I am trying to do is make AWS the most expensive place to target. Right? If you target AWS, we will take down your infrastructure. And if you target us again, we'll do it again. And so that allows us to make us a less attractive place to target with DDoS. But we take this even a step further. So now, remember I said we had the malware, right? The malware runs in a sandbox. It registers out to the C2, and then we know where the C2 is. But now we also have our own little DDoS bot, right? This bot just sits there. And when C2s send commands, our bot gets it. And so immediately, now we have almost a feed. We have a feed of C2 commands. These C2 commands just come in like you won't believe, right? We're seeing millions of DDoS attacks every year. We get commands coming in that look like this. Usually, once you've distilled down from the packet to what the command is, it's got some type of vector or protocol that should be used in the DDoS attack. It's got the destination IP and port. So, of course, we're looking at these destinations going, oh, this destination's on our network, right? So now someone's like knocking on our door saying, we're about to hit you with a DDoS attack, right? That's like early warning notice for us. And then usually the malware has a bunch of parameters that you can pass in for attack duration. Maybe, it could be hit them, like target for 5 minutes and then stop and then start again for 5 minutes. And so it's got various types of parameters. And so, we're getting this feed, and that's allowing us to place mitigations before the first packet has even hit us, which is outstanding, right? So we're driving up cost for bad actors through this research, and we also are improving our ability to be proactive in DDoS mitigations. You want to talk about DDoS resilience?
I do. So this last section, we wanted to try and give you some practical advice on how to think about making your application as DDoS resilient as possible, which I know that was the title of the presentation, so we thought we should probably address it. So the point of giving you all of that insight, though, is to show you there is a lot that goes under the covers to mitigate DDoS automatically. So when Shield is working and does its thing, you shouldn't have to worry about DDoS, other than there may be small periods where you have to scale up briefly in order to take on additional traffic. Right? So there's a ton of stuff that will just happen. There is a big difference between Shield Standard, so-called. Everything that we've talked about here is Shield Standard, meaning these are infrastructure and service level provisions. So we monitor things CloudFront-wide, distribution-wide, service-wide. We don't look at any specific customer resource. Whereas Shield Advanced is all about monitoring your specific resources, understanding your resource capacities. And so that's the big difference. Plus, you get access to Paul's team, who will help mitigate things where the technology doesn't work perfectly. But there are some best practices that we strongly advise you think about as you're designing and operating your own infrastructure. I'm particularly proud of that animation, by the way. Do you want to see it again? The first one is architecting for resilience. What that means is using services in a way that will help you with resilience generally, not just from DDoS, but any kind of failure, right? So, we have this concept of availability zones, and an application that's built in more than one availability zone, or potentially across regions. That's not necessary for availability, but there may be other reasons why you want to expand across regions, are going to be fundamentally more resilient than if you build everything in a single availability zone. And so, it really helps to understand how your application will deal with any kind of failure all the way through, and that's architectural decision. And those are those things that your SAs and TAMs will be able to help with, but Paul's team will also be able to help with if you're a Shield Advanced subscriber. The next one is using services that we provide in the edge for huge scale. So we talked a bit about CloudFront. CloudFront is massive. I don't have a better word for it. I mean, these services are built on a truly global scale. Global Accelerator is another very, very highly scalable entry point service for traffic that is not purely HTTP. So if you've got other kinds of network traffic, Global Accelerator will give you static IPs anywhere in the world. It will use any cast to distribute your traffic, so only using the backbone to bring the traffic from that ingress point back to your region, and so it's a latency enhancement product as well. And Route 53, if you were thinking about running your own DNS service, I strongly advise that that might not be the best way to do it, because these things are so huge, so resilient, and so scalable. The next piece to think about is monitoring. So you have to understand your traffic flows, right? Quite often when we engage with a customer and they ask for help, it takes us a while to understand, if we haven't engaged with that customer ahead of time, which we would like to do, by the way, we'd like to understand your architecture. That helps us, help you. But, understand where the points in your application architecture that you need to monitor. What are your points of throttle that you need to monitor and to figure out what's going to break? And we'll come on to health checks in a second, but there are ways that you can use these metrics once you understand what your key metrics are to automatically page in Paul's team to come and help for that. The next one is using scalable components across the whole stack. There's no point in having a fantastically scalable front end. You've got ALB there, which will scale up automatically as your traffic increases, if your origin can't handle that. You need to make sure that it's scalable all the way through. And ideally, that you've tested that and you understand how that is going to scale and what the properties are. How fast can it scale, for example, and what might break. Again, going back to the monitoring, if you get a very unexpected fast peak, what's going to happen? So these AWS components are built for massive scale, and so make sure that you're not putting 3 highly scalable services on the front of a single Nginx server. That's not going to help. Next one is defining your security model. So we provide a lot of security tools, and sometimes I know that can be a little bit overwhelming when you can do multiple things or the same things in multiple places. My advice is to try and block traffic you don't want in your application as close to the edge of the network as possible. So Shield is the ultimate example of that. We can block traffic really as it's entering our network through our network peers or our POPs. And the product that I mentioned, the regional protection, will be able to create more always-on mitigations. So that's something you'll be able to do to say, block this traffic, so it never even gets to your infrastructure. You don't pay the cost of that. So the earlier you block it, the less cost you incur having to drag that traffic through your network to block it later on. So network access control lists are an important tool at your VPC level. WAF is a very, very powerful tool for blocking traffic, both static rules, but also more dynamic stuff. We have Paul's team provides the threat intelligence for the managed rules, some of which are updated every few minutes. So there's a list of known bad actor DDoS offenders. There's a better name for it than that, but it's a list that we update every 5 minutes from all the attacks we're observing across the whole of the AWS network surface. And so you can say, I don't want these guys in my application, so you can just place a block on that, and we'll manage the rest. Network firewall, also a very, very powerful tool for other traffic other than HTTP. And then Firewall Manager, which helps you bring all of that together and manage that at scale across all of your accounts. And then the last one is how you interact with the Shield response team. So we have a system where you can set up health checks, which will tell us when your application is impacted. And that will correlate that with network traffic that we think is causing that impact, and we'll cut a ticket, a high priority ticket to Paul's team. So they will get involved potentially before you even see that impact yourself. So it's a very powerful tool. Then one of the first things they will do is reach out to you. There's proactive response. So we need to make sure we've got the right contact deals. How do we get hold of you? Phone numbers, email addresses, pages, all that kind of stuff. So that we can then engage and rapidly get behind anything that needs to be done from a mitigation standpoint. And we can place these very advanced mitigations, things that aren't necessarily available through the console or that you can't do on WAF. We can build very custom mitigations for you as a Shield Advanced customer. That can either something that's always on, which is ultimately the best defense, means those packets never reach your application, or something that's proactive in order to deal with an active attack. And that's what we've got. I think we will hang around for a period to answer questions if anybody's interested. We would very much like to get your feedback on this session. So if you can use the app to provide some response, if there are things that we didn't talk about that you would like us to next time we do this, we would like to know that. And thank you all very much for coming.